speed day, an hour and a half into class. Isn't that great? No. So where we are today, the idea is just a sample. Okay, so this week is it's kind of a light week. You just had a quiz because you have this assignment that's 2 weeks long. So we're going to talk about just a sample. So 2 things that we're really going to talk about: data cleaning and sampling. Okay. Really, let's do this in the other way. We're making changes on the fly. Let's start with sampling first. First question. Sampling. What makes a good sample? I've got blue guys and green guys. Yeah. What makes a good sample?
It's representative.
Sample has a characteristic of population, the attack population.
Alright, so we've got representative. Population, sample, characteristics. What else makes a good sample?
No outliers.
Ooh.
Yeah, the probability of finding that sample in the population should be, how do I put that? So I mean, we may find a sample, but with the right characteristics. But what if it's rare?
So you should be able to replicate the sample, right? Be able to get, if I did multiple samples, they should have similar outcomes.
Yeah, something.
So not just some weird outliers samples, but like a representative sample. Okay? What else? What makes a good sample?
It has to be. Okay.
Bias. No bias.
No what?
No bias.
No bias.
Bias.
No bias.
I'm good with that. Okay. Bias.
It has to be large enough to show variation.
Large enough. Good. Anything else? Anybody's just like, to be a good sample.
It should be random.
Oh, random. I like representative. I think that's great. We definitely want a representative sample. They should have similar characteristics, right? I agree. We should be able to replicate the sample, right? So we shouldn't just have like a weird, funky sample. Large enough. I like that one. How large is large enough? It depends.
Isn't 30 kind of like the standard number to like get a normal bell curve, like a simple random sample of 30?
30 is a magic number. We will talk about why 30 is a magic number. Who said it depends? I didn't say it, but I thought it. It depends. Another good. So when you get into more advanced statistical classes, experimental design, you will actually have charts that, given how confident you want to be in your results, given a few other conditions, you will get to determine what is the appropriate sample size for your data. And again, to make statistical inferences. Okay, that's what we're focusing on. We have large data. When we have large data, do we need to take a sample? Should we take a sample?
Yeah.
Why? If I got all the data, why would I want to take a sample?
One that has the ability to work with the data is such a large amount.
Okay, so if it's too big, then maybe I can't do too big. So maybe I do want a sample. But if I can work with it, my software, it'll handle 1 million rows. It'll handle 3-4 million rows. It might take a little bit, but it'll do it.
Typically, if you want to make a model, you want to play with a limited amount of data, which is representative, so that, I mean, I'm just going conceptual. So that if I change one of the factors, then I want to see the impact of the change. It's easier to work with smaller data set rather than 30 millions.
So if I'm trying to model something, we'll do that at the end of the semester, right? If I'm trying to model something, maybe I want to model with this part of my data and then test it out with this other part of my data. Okay, I like that. It's a good reason to sample. So let's say I have those billion, do you have a billion? I think I have a billion rows in Sam's Club. I have a billion transactions. Yeah, B with a billion. Okay. Even if I just had 1 million transactions, would 30 be enough? Would 30 be representative of my, let's go this way, would 30 be representative of my 100 transactions?
Yes.
Assuming we get a good sample, would 30 be representative of 1,000 transactions?
Probably.
If I had a really good sample, would 30 be representative of 1 million transactions?
No.
I was trying to figure out where your breaking point was. So then, but if we had 1 million transactions and I actually had access to them, then would I really be doing inferential statistics? Or should I be doing something else?
Right.
Stay tuned next semester for data mining. Once we start to have large data, then we have to start rethinking our ideas of inferential statistics. Okay? So right now we're going to say we have smaller data, and we're really trying to do some inferential statistics. We want a good sample. We want it large enough. Okay? Is it problematic if we have outliers in our sample? Not necessarily. If we assume there's outliers in our population, then we got an outlier in our sample. Okay. That could be okay, but given, I'm going to put these two together, but what if we had a lot of outliers? Right, we had that rare case, that weird sample. Then maybe not. When you talk about bias, what kind of bias are you talking about? Anybody can jump in on this.
Convenience.
Convenience? So how I got my sample?
Yeah.
Okay.
Conclusion bias.
So conclusion, what do you mean conclusion bias?
Well, manipulating the data to better suit the goal that you're looking for.
Okay, so cherry picking my sample?
Exactly.
Okay.
Bias because
Response bias, like how I responded?
Or like how you like word the question.
Oh, so I can have a bad instrument getting my sample data. Okay.
I think bias because bias in sampling itself, in the sense that instead of taking my sample is let's say Sam's Club operates in Canada and USA, or probably West Coast and East Coast, but I took samples only of East Coast and thinking that it's going to be representative of the entire country.
So not representative. Yeah.
Because I have access to it or whatever.
Okay. So bias in terms of what I do. Okay. Will bias get into your data sets from a respondent perspective? I'm not going to do this, but if I threw out a political question, you inherently are going to bring your personal bias to the answer of that question. right? So you can't get rid of respondent's bias, but we can mitigate our sample collecting bias. Okay. So no bias. I like that one a lot. Random. That's the one everybody's wondering. I want it to be random. Does it have to be truly random? Fake it like it's random? Random enough? How can we get random samples? Make it easy. If you are my population and I need a sample, how can I randomly get you all? How can I randomly get my sample?
Like a random number generator, like assign everyone a number and then just randomly pick.
Sure. Right. Assign everybody a number, randomly pick it. Okay. If I wanted to do something, I need to group you guys up. Well, maybe I'll do that for your groups. I won't do that for your groups. Okay. So random number generator. Okay. And could I use that even if I had a bigger sample? Right? Even if I had 1 million data points, it'd be harder, but I could still do it. How else could I get sample data? Try to make it random. All right, I've got slides. Okay. Before we get to, we're going to play back and forth on this one. Okay, so let's go talk about some chapter 7 stuff, and then we'll come back and do a little more motivation stuff. Okay, vocabulary. We've talked about populations and samples already. Everybody knows what they are. We are going to get a little more detailed about the populations, right? So we got the population, big group, sample, small group. The population, we have a target population. That's who we want to make inferences about. But just because I want to make inferences about a group doesn't mean I can actually get a sample from that whole group. Okay. So there's a targeted population, there's also a sample population. That's who I can actually get my sample from. Okay, there's a little bit of a distinction there. Our sample is just a subset of our population. And the idea here is that our sample is going to provide an estimate. Okay, all that we're doing are making estimates. Our best guess given what we got. Okay. People occasionally make a very big deal about sampling between a finite population and an infinite population. We just want to keep in mind that those are a little bit different. We're not going to get into the math of how to do it. Okay. But when there's a finite population, you can assign everybody a number, do a random number generator, that's great. But when you have an infinite population, like in a manufacturing place, right? Things are coming down the line and you have an infinite number, like you're just going to keep making things. Well, I can't just assign a finite number and then randomly pick it because there's more coming, right? So what if I want to sample the ones that we make tomorrow? Okay. So the difference between a finite and an infinite population, we have to be able to do and sample all of those different things. A couple of different sampling methods. Some you may have heard of, some you may not have. So random sampling, that's the thing everybody wants. But actually getting it becomes a lot harder. Okay? A stratified random sampling, right, kind of addresses the idea over here. I want to make sure not just that I get a random sample, but that I get all of the representative people. Right? So in this class, I wouldn't just want to number everybody 1 to 30 and randomly pick 5 of you. Okay? I may want to have all of the MIS and then randomly pick a couple, and all of the max and randomly pick a couple. And we only have a couple of stands, right, in degree program. And so the probability that I would get a stand student is much lower than the probability that I would get an MIS or a max student. Okay? A stratified sampling, we put people into strata, right? Freshman, sophomore, junior, senior. Undergraduates, grads. Males, females. different races, different ethnicities, different religions, different political backgrounds. We make sure that we stratify people, and then we take a random sample from each strata. So that way we don't end up with all grad students and no undergrads, or all undergrads and no grads. Okay? If the strata are homogeneous, right, then we can actually get away with a smaller sample size than if we just do random sampling. If I do random sampling, then I want to have my sample large enough that I make sure to get people. But if I stratify, then I just need to have 2 from this group, 2 from this group, 1 from this group, and now everybody's represented. Cluster, yep.
So what do you call it? Stratified. So before we embark into that, the whole process of picking the samples, do we then first determine what is going to be my stratas in the pop? So then we go back to the question: what are the criteria that we have to?
Absolutely. Right. So we can answer the same question with multiple samples, depending on if I'm interested in, is it a gender thing, is it a political thing, is it a education thing, or do we want to interact all of those to make the best possible sample to have all the strata represented? So yeah, so you would decide that ahead of time, what matches your business question, and then you would go and find the information out of it. Okay. That works best for a finite population. Right? You wouldn't stratify infinite because it's just going to keep on coming. Cluster sampling. This works really great when it comes time to vote. And it works really great in school systems. Honestly, it works really great in retail. Really, it just kind of works really great. Okay. So a primary application is area sampling, where clusters are city blocks or well-defined areas. The idea of cluster sampling is instead of taking the entire state of Arkansas and randomly sampling people from all over the state, okay, or randomly sampling stores from all over the state, the idea would be to find areas, randomly select areas. Therefore, those areas should be represented, or those stores should be representative, and then randomly select from within those areas. Right? So instead of randomly selecting the whole big population, you can randomly select an area, and then randomly select from within that area. So when you're doing your polling data, they don't go out and randomly select people all over the state. They find representative polling places, and will randomly select people from there. Systematic sampling. I call this phone book sampling. Oh, it's even the example. Right? You look at every 100th listing in this phone book. Okay, that's going to be your random sample. Right? Here's my list, and I'm just going to pick, or if I wanted to pick people, you're walking through the door. Every 5th person that walks through the door is part of my sample. Okay? You're assuming that that is a random distribution. Easy to use, but you can run into issues if you think about it from a phone book perspective. Right? If you only want 100 people, and you start with the A's, people at the end of the alphabet, sorry, you're probably not going to make my sample. Right? Or you start with the Z's, different, go backwards. But still, once you're going with 100 people, you're going to run out of. So you got to make sure that if you're going to do that, you have to have the whole sample, for the whole population, and then figure out the best sampling method there. So systematic sampling, convenience sampling. Who said convenience sampling earlier? Yeah. Convenience sampling is the easiest one to get, and the one that's kind of gotta be careful about. Right? These are the people who ask you questions at the mall. They still do that. Right? Talking to them all and be like, hey, what are your feelings about this new product? Okay, so convenience sample is really the sample that is identified primarily by convenience. I want to know about Walton students, Walton graduate students. You are my sample because you're in my class. Convenient. Okay. When you call in, how many of you guys, be honest, American Idol, The Voice, dancing shows, you've called in at least once? Seriously? No? Like, this is not a thing anymore? Because they're on TV all the time. It's not a thing. Like, not even the guy from Arkansas? Like, nobody... Seriously? Well, that just blew up in my face as far as I'm concerned. But you know what I'm talking about, right?
Yeah.
So even if you don't call in, or do you text in?
Like your vote?
That's your vote.
I mean, I haven't.
Oh.
Well, I know what you're talking about. I was confused with saying calling. I was like,
Well, I realized that. I'm like, nobody uses their phone anymore. Okay. So did you text in? Text in and say, oh, I really like this person. Keep them around. Nobody?
sure.
Thanks.
I've seen it.
Yes. I've seen it done.
I've seen it.
I've seen it done. I know somebody who did it. I didn't do it. I did one semester, one season of American Idol. I did text in, but it was because I knew the girl, so like I felt bad for not texting
Did
in.
you win?
Top 3.
Whoa.
Oh, she was pretty good. Who won that year? It's on the radio. Yes, I know, right? That's what happened. You guys roll with it today. I'll think of who it was in a minute. But yeah, anyway, so top 3. So yes, I did. So the year I taught that, I was like, hey, yes, this is awesome. So the convenience sample, right? It's just the people who call in. So you may have some very strong opinions about whichever of those shows you now have no time to watch. But you don't call in, so your voice never gets heard. So it's only the people who have friends that are calling in for them, or the people who are just like diehard, like. Okay, so it's a convenience sample. It's just the people who call in. A judgment sample. This happens more in academia. It could happen some in retail. Actually, this may be accountants. This may be yours, right? A judgment sample. Right? So the most knowledgeable person on the subject is the one who's going to select the pieces that he or she feels as most representative of the population. Right? So if you think about it like a doctor's case study, right? I treated all these patients, and if we're going to do a case study, I would select these 4 patients because they are the most representative of what I've seen. Right? This happens a lot. I can see this happening a lot, like in retail, right? So here's all of our stores in Arkansas. We're not going to go to all of our stores, but these 4 are the most representative of our stores as a whole, so let's go investigate these 4. Okay, so judgment sampling. Here, a reporter might sample 3 or 4 senators, judging them reflecting the general opinion of the Senate. Okay, so it depends on the judgment. Who is the expert? Okay. And are they really, so we don't know that they're really representative. These are just all sorts of different ways that we can do sampling. Most popular ways that have made it in textbooks. You can make a living out of just getting good samples. Right? I have a friend that works for the U.S. Department of Agriculture, and they work on census data. And they work on finding the best samples to get representative information from our census data. All that census sample. Whole course. But as we're getting these samples, the whole idea is we're getting these samples so we can get an estimation of our population. So these point estimators. Next week, we'll talk about interval estimators. This week, point estimators. So we haven't really talked about notation. Other than the 3rd week of a stat class, I feel notation we should do. When we're talking about samples, we use Greek letters. Everybody good with this? You all know this, right? Why we don't talk about it? When we're talking about populations, we try to use Greek letters. Right? So samples are more Roman letters, populations are more Greek letters. Okay, so X bar is the point estimator for the population mean mu. I learned it's not mu. You actually talk to a Greek. Mu, like cows. I call it mu all the time, right? That's, if you're in the Greek system, it's mu. But if you're from the Greek islands, it's mu. Okay? S is the point estimator of the population standard deviation, sigma. Yes, that is it's a lowercase sigma, not the capital sigma. Again, Greek thing. The P with a bar over is the point estimator of the population proportion. And that is actually just a slanted, italicized P. It's not a Greek letter. Okay. Easy enough? Yay. Let's do an example. So, St. Andrews College, 900 applications. Applications has stuff from the SAT, whether you want to live on campus or not. We've got, again, 900 applications, so we numbered them 1 to 900. But our data didn't all get put into our database yet, but I need some results for this meeting that I have to go to this afternoon. So just randomly give me 30 of what we have. We'll get the results there, and then we'll get the rest of the database later. Okay? Is that an okay thing to do? Yeah. I'm taking a sample of my population. Okay, no problem. When I do that, let's start over on the right-hand side. So when I do this, here's my sample of, what did I say, 30 people? Okay. So my sample is, I've got an SAT score of 1684. I've got a standard deviation of 85.2. And the proportion of people wanting campus, on-campus housing is about 67%. And that came from my 30 people. So I go to my meeting, I'm talking to the dean, this is what I can tell him, we're going to make a few decisions, okay? Then, finally, a couple days later, we get everything entered, and we come back and we say, how close were we? Okay, so our population, when I have all 900, right, actually my SAT score for these applications is 1697. I said it was 1684 for my sample. Not too far off. Our standard deviation was 87.4. Here we've got 85.2. Here, our population wanting campus housing. So really, there's 72% who want campus housing. I told you 67%. I was a little under, but for the most part, not too far off. So hopefully I had a good sample. I can go to my meeting, I can make some decisions, and then I can learn more like. Everybody comfortable with that? Okay. So that's just point estimation. So when we have a sample from our population, we can just make some point estimates. Okay. The next thing we can do is what happens if I take a different sample of 30. Right? I had 2 GAs working for me. I said, hey, can you do this task? One group randomly selected 30, and another one randomly selected 30. Well, that time my point estimate was 1689 was 88.3 and was, what's the difference? 0.7. Now, whose data do I take? Do I take the first, or do I take the second into my meeting? I average an average.
Or you could probably say between this and this.
Oh, so what you're saying is you don't want just one number. You want maybe like a range of numbers. But what if I did a different sample? And then a different sample, and then a different sample. This is the idea of a sampling distribution. So this is the math part of stuff for today. So with the sampling distribution, what we have going on is we're going to take, right here, where our 30 comes from. When I have a sampling or when I have a distribution of data, okay, a lot of the stuff that we're going to be doing for the rest of the semester is going to make this assumption that we have data that are normally distributed. We like that bell-shaped curve. If we have that bell-shaped curve, there's a lot of things we can do with it. But a lot of data aren't normally distributed. Okay? So what we can do is we can take one sample, and then we can take another sample, and then we can take another sample. And if we actually take multiple samples, then eventually our data will become normally distributed. And that's the whole idea of this thing called the central limit theorem. You do not need to memorize the central limit theorem. You're not going to be tested. Oh, take that back. You will not be tested on the central limit theorem. You might be quizzed on the central limit theorem. You won't be tested, but you might be quizzed. Hint. For our central limit theorem. And basically what it says is when we start selecting a bunch of different samples from our population, and we start plotting the means, then once we have about 30 of them, okay, it's going to start to be approximated by this normal distribution. And as part of the central limit theorem, what we get to do is we have this thing called the standard error of the mean. And basically what we're doing is we're taking the standard deviation of the population, and then we're factoring how many samples we've taken. And that's going to change what our distribution looks like. And the best way I could think to do this was just to show you some examples. Okay? So what we've done, my first sampling, okay, we had a SAT score of 1697. That was my average. Okay? And I had a sample size of 30. So what I have here, this is my standard deviation. I have, you can't see that. Here's my standard deviation, right here. We take the square root of the sample size, and that changes the standard deviation a little bit. Okay. So when I have a sample size of 30, my standard deviation, my standard error of my mean is about 16 points. So I'm just looking at 1 point, so just 1 point estimate. Then I've got a 1697, and I've got about an 87 point range in my scores. But now that I have a sample size of 30, now my standard deviation, my standard error of my mean is about 16 points. Questions that we ask. We start talking about probabilities, right? What's the probability that if we take some simple random sample of 30 applicants, we're going to have an estimate, a mean SAT score that's plus or minus 10% of our actual population mean. So we go plus or minus 10%. So our actual population mean is that 1697. We go 10 points below it, we're looking at 1687. We go 10 points above it, we're looking at 1707. Here's the steps of what we're going to do. I'm not going to go through the steps, I'm just going to show you. So really what we're doing is we have this distribution. This is our population mean right here. That is my best attempt at drawing a moo with this pen. The first thing you're going to do is we're actually going to look for that z-score. We're talking about a normal distribution. So we look for the difference between here. So this is a z-score of 0. And we can calculate the z-score here to be 0.63. And ultimately what our goal is going to be is to find the probability between here, what was the other number we said? 1687? And we want to figure out how much area is between these 2 points. In real life, that's a Cal 2 problem. How do you guys taking Cal 2? Integrals, area under the curves. In stats class, somebody already did all the math for you. There's this fun little table. You can use this table. That was in the old days. Now we have computers. All we have to do is say, hey, I've got a normal distribution with a z-score of 0.63, and it'll tell you what the probability is. Lots of fun. But our goal, again, I told you this is going to be the most mathy part, is trying to find that probability. So we find the z-score on one side, and then our book, what it tells us is the area below that score is about 0.73. Well, then my next step, right, so we already have this 1707 with the z-score of 0.63. If we go below, we can find the z-score, and it's negative 0.63. My book will tell me that this area down here is about 0.26. But remember, I'm actually looking for this blue area. So I gotta do a little math. And my next step says, if I take all of the blue area that I know, and that is 0.7357, and then I subtract out the green area, 0.26, then I'm actually left with the red area, which is what I'm interested in, which is 0.47. You guys done this before? Everybody good with it? This will make my job easier. So really what we've just done is figured out that the probability that we've got this estimate of the population, and our scores are going to be between a 1687 and a 1707, is about 47%. And sometimes knowing those kind of questions is important. Right? How do I make decisions? Well, I want to know, what is 50% the other way? Right? What values hit at 50%? What values do I cover 75% of my data? So we can actually use this quite a bit. When we increase our sample size, right? We have 900 people in our population. I just took a sample size of 30. If I increase my sample size to 100, okay, then what I've done is with my sample size of 30, my standard error of the mean gives me a distribution like this. My standard error of the mean is about 16 points. But when I increase my sample size, now my standard error of the mean becomes smaller. I love that I'm the one whose phone always goes off. I mean, that's just priceless. Okay. So now, instead of having my data all spread out, because remember the goal here with sampling, right, is to get closer and closer to my true population mean. Okay, 1697 is what I have. If I get all 900, I've got a 1697. Well, when I start out, if I'm only sampling 30, I've got a pretty wide range. Now if I sample 100, my range has gotten a little bit smaller. So if I had to approximate, this is just me guessing, if I had an N of 500, what do you think my distribution would look like? Yep, we're going to go taller. I still got that 100% of my data there. So like that. And eventually when I get all, this is the easy part, my sample size is 900. It is right on. Okay. There's no error of my mean because I've got my true population mean. Okay. So this idea, this standard error idea, is going to play out for the rest of the semester. So what we're going to be doing, right, is we're going to take this idea and we're going to take some value, whatever it is. We're going to find the difference between it and some other value. I'm going to be very vague right now. Okay. And we're going to divide it by this standard error. In essence, that is a z-score. In essence, that's a t-test. In essence, that is an analysis of variance. A lot of the tests that we're going to do throughout the rest of the semester, this is the idea. Okay? We're either going to take two means and find the differences, we're going to take a raw score and find the difference between a mean, and then we're going to divide it by some type of standard error that takes the sample size into account to be able to figure out, we'll get to the probability points and saying, okay, is this extreme enough? Okay. So this is an intro preview into what we're going to do for the next 14 weeks. Okay. There's that. Okay. So now let's go back to, real quick, a little more motivation. We can't do any of this stuff unless we have data. But we gotta have good data. If we're gonna take all the time to get a good sample. Once we have a really good sample, now we need good data from that sample. Okay? So when you're thinking about looking at a data set, what kind of issues can you think of that can mess up your data set?
Missing value.
Missing values.
Wrong categorization, especially dates.
So wrong categorization. They got stuck in the wrong category.
Especially dates. Yeah.
Oh, so also, so like formatting stuff, right? Like date formats?
What I was saying, there is something dates are saved as text and they don't change it to date. So that becomes a real mess when you're trying to do it.
Absolutely. Right, so that date format, so if you're trying to look at the day, if you're trying to look at the month, if you're trying to look at the actual day of the week, like so many different dates are a pain. We're going to play with those in a little bit. What else? What other things can you think of that have issues?
Duplicate values.
Duplicates.
You can have a number that's like entered wrong.
Just entry errors.
There's an essay response, like figuring out how to like group and categorize those. So how different.
Let's say categorizing text. I'm going to add typos to data entry errors.
I won't say this as an issue, but sometimes data needs to be massaged before you can, like, they are in different tables, product ID instead of product name, customer ID instead of customer name. So some sort of data massaging will have to be done from various sources also, maybe.
Data doesn't match. We need to massage it. Some of this stuff we'll deal with. Some of this stuff is more for your data analytics fundamentals class. So extracting it correctly, getting the tables to go together. Two tables don't go together. That was our big issue. We were trying to combine some stuff in our Sam's Club database not too long ago, and we had two different date formats. That's some issues there. Okay, so those are a few things. There's a video set, if you want to look at it, for this week that has a few more things. It's like less than 10 minutes total. I started just doing some research last night. Data quality problems, right? You got your single source problems, which is what we mostly started out with, and then we got into the multi-source problems. Right? So lack of integrity constraint, poor schema design, right? Uniqueness, referential integrity. Right? This refers to this, but this also refers to this. So if I try to do this, I don't know which I'm getting. Right? Data entry errors, those are the big ones, right? Misspelling, redundancy, things that contradict each other.
What do you mean by schema design?
For me, it's just like how your data are set up, right? So the schema behind it. So when I set up my data, I think of, for our Razorback data, right? I say my loyalty customer, I said it was a 1. If they're not my loyalty customer, I say it's a 0. You are going to come in and enter data after me. You think a loyalty customer is a 0 and not a loyalty customer is a 1. So now because our schema has not been defined and kept consistent, lots of issues.
Okay.
That's actually what I did for my PhD. My first year, the entire year was spent taking people had entered data in 3 different data sets and I had to combine them. And it was wrong. Some people entered things 1 to 5, others did 5 to 1. Some people recoded values, some people did. Just all this craziness trying to be able to feel comfortable with your data to be able to make a decision. Yeah? Okay. That was a fun year. And that was before I learned all the cool stuff that you guys are learning. It was a painful year. Right, when you get to the multi-source stuff, right, you got naming conflicts. So in this table it's named this, in this table it's named this. In this table I have a 5-digit ID, in this table I have a 6-digit ID. For the same thing, right? Overlapping, contradicting data, inconsistent data, missing data. We're going to run into all the issues.